The British Museum basement in London, 1945. Winter light filters weakly through high windows, illuminating dust motes that dance like ancient spirits above rows of storage shelves. A young mathematician named Otto Neugebauer sits hunched over a clay tablet no larger than his hand, his eyes straining in the dim light. The tablet is covered in cuneiform wedges, pressed into soft clay nearly 4,000 years ago by someone whose name has been lost to time. But the numbers tell a different story. Neugebauer's pencil hovers over his notebook. His hands are shaking. Not from cold, though the museum's heating system barely functions in these austere post-war years. He shakes because he has just realized something impossible. These ancient Babylonians, working by oil lamplight in mud brick observatories along the Euphrates River, had calculated the movement of Jupiter with such precision that their predictions would remain accurate for centuries. More than that, they had developed a mathematical system so sophisticated, so elegant, that it would take modern scholars decades to fully comprehend its depths. This is the moment when ancient history splits open like a pomegranate, revealing seeds of knowledge we thought impossible. This is the moment when we begin to understand that the story of human intelligence, of human consciousness, reaching toward the stars, is far older and far stranger than we ever imagined. Close your eyes for a moment. Imagine the night sky as our ancestors saw it, unobstructed by light pollution, unfiltered by the haze of modern civilization. Imagine darkness so complete that the Milky Way casts shadows. Imagine stars so bright they seem close enough to touch. Now imagine looking up at that cosmic tapestry and deciding, without computers, without telescopes, without even the concept of modern mathematics as we know it, deciding that you will map it all, that you will predict the movements of planets, that you will calculate eclipses years before they occur, that you will decode the language of heaven itself. This was the audacious dream of the Babylonian astronomers, and against all odds, against every limitation of their time and technology, they succeeded. But here is the mystery that will occupy us for the next 2 hours. Here is the question that burns like starlight through the corridors of lost history. How did they do it? And perhaps more importantly, why have we forgotten them? Why do we speak of Greek astronomy as the beginning, when the Babylonians had already perfected these arts 1,000 years earlier? Why do we celebrate Ptolemy and ignore the nameless scribes whose calculations made his work possible? Tonight, we embark on a journey into the deepest past. We will walk the streets of Babylon when its walls touch the clouds. We will stand in the observatory towers where men and women track the wandering stars across decades of patient observation. We will hold in our minds the clay tablets that preserved their genius across 4 millennia, and we will discover that the line connecting ancient Mesopotamia to NASA's Jet Propulsion Laboratory is far straighter than anyone ever imagined. This is not simply a story about mathematics, though we will encounter mathematical beauty that will take your breath away. This is not simply a story about astronomy, though we will watch the heavens through ancient eyes and see patterns that revolutionized human understanding. This is a story about the unbroken chain of human curiosity, about knowledge that refuses to die, even when civilizations crumble, about wisdom carved into clay that outlasted empires. The forgotten mathematicians of Babylon were not primitive stargazers stumbling in the dark. They were architects of understanding, engineers of time itself, prophets who read the book of heaven with such skill that their predictions echo into our present day. They developed a base 60 number system so perfectly suited to astronomical calculation that we still use it every time we tell time, every time we measure angles, every time we look at a clock and see the hours divided into 60 minutes. Their legacy is all around us, hidden in plain sight, waiting to be recognized. But before we can understand their achievement, we must first understand what was lost. We must feel the weight of forgotten knowledge pressing down through the centuries. We must trace the thin thread of preservation that kept these secrets alive through the collapse of empires, through the burning of libraries, through the dark ages when the very ability to read cuneiform vanished from Earth. And then we must ask ourselves the most dangerous question of all. What else have we forgotten? What other knowledge lies buried beneath the sands, pressed into clay tablets still waiting in museum basements, encoded in astronomical observations we haven't yet learned to read? The desert wind that blows across the ruins of Babylon carries questions older than memory. Questions about who we are, where we came from, and what we're capable of becoming. Questions that can only be answered by looking backward, so far backward that we can finally see forward again. The story begins in darkness. The story begins with someone looking up. The year is approximately 1800 BCE. The place is Babylon, jewel of Mesopotamia, where the Euphrates River carves its way through the cradle of civilization like a silver serpent. The city rises from the alluvial plains in a statement of human defiance against the horizontal emptiness of the landscape. Walls, temples, gardens, towers that climb toward the realm of gods. But we are not interested in the ground. Not tonight. Tonight, we climb. Follow me up the narrow stairs of a ziggurat, the great step pyramid that serves as temple, observatory, and monument all at once. Our feet echo on sun-baked brick as we ascend level after level, leaving the noise of the city behind. The air grows cooler as we rise. The voices of merchants and priests fade into the general hum of urban life below. By the time we reach the summit platform, we have left the world of men and entered the domain of gods. Or so they believed. But what they found here, what they discovered through patient observation and brilliant deduction, was something even more profound than divine revelation. They found the mathematics of heaven itself. A figure stands at the platform's edge, silhouetted against the dying light. He is a scribe, a member of the specialized class of scholars who serve the temple. His hands are stained with the clay he shapes daily into tablets. His eyes carry the particular weariness of someone who has looked at numbers for so long that they appear even when he closes his eyes to sleep. His name, he is not simply an ancient astronomer indulging his curiosity about the night sky. He is here because the priests have given him a sacred task: predict when the moon will vanish from the sky. Predict when the red star of war, which we call Mars, will reverse its course among the fixed stars. Predict when Venus, the bright herald of dawn, will appear and disappear on its eternal cycle. Why? Because in ancient Mesopotamia, the movements of celestial bodies were not mere scientific curiosities. They were omens, signs, messages from the gods written across the vault of heaven in a language that only the learned could read. A lunar eclipse foretold the death of kings. The position of Jupiter determined the fate of nations. The appearance of comets announced changes that would reshape the world. But here is where the story becomes interesting. Here is where ancient superstition transforms into something else entirely. Because in order to interpret these omens, the Babylonian astronomers had to predict them. And in order to predict them, they had to understand them. And in order to understand them, they had to observe them with such rigor, record them with such precision, and analyze them with such mathematical sophistication that they accidentally created something revolutionary. They created science. Not the word, of course, not the concept as we understand it, but the method, the practice, the patient accumulation of data across generations, the search for patterns in that data, the development of mathematical models to predict future events, and the constant refinement of those models when predictions failed to match reality. Night after night, year after year, generation after generation, the watchers came to their platforms. They carried with them fresh clay tablets, styluses carved from reeds, and instruments for measuring angles and time. They noted the positions of planets relative to the fixed stars. They recorded the intervals between new moons. They tracked the rising and setting times of significant celestial bodies. They compiled vast catalogues of astronomical phenomena spanning centuries. And slowly, pattern by pattern, calculation by calculation, they began to crack the code. The earliest astronomical texts we have from Babylon date to the Old Babylonian period, around 1800 BCE, but they reference observations going back even further. These texts reveal a civilization already deeply committed to celestial observation, already developing the mathematical tools they would need to make sense of what they saw. Consider, for a moment, what they faced. The night sky is not a simple thing. To the untrained eye, it appears chaotic. Stars wheel overhead in their eternal circles. Planets wander unpredictably among them. The moon waxes and wanes according to some mysterious schedule. The sun traces its path across the sky, higher in summer, lower in winter, but never quite the same from year to year. How do you find order in this apparent chaos? The Babylonians began with the most obvious cycle, the day. But they didn't simply divide the day into arbitrary segments. They developed a sophisticated system based on the number 60. Why 60? Because 60 is a highly divisible number. It can be divided evenly by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. This makes it perfect for fractions, for calculations, for the kind of mathematical work required in astronomy. They divided the day into 12 double hours. Each double hour contained 60 minutes. This base 60 system, which we call sexagesimal, would become their mathematical lingua franca. It would allow them to express fractions with elegant precision. It would enable calculations that would be cumbersome in a base 10 system. And it would last. It would outlive Babylon itself. It would survive the Persian conquest, the Greek triumph, the Roman expansion, the Islamic Golden Age, the European Renaissance. It would arrive in our modern world intact. Every time you look at a clock and see 60 minutes in an hour, you are looking at a gift from Babylon. But the day was only the beginning. Next came the month, defined by the cycle of the moon. From new moon to new moon, approximately 29.5 days. The Babylonians tracked this cycle with such precision that they could predict new moons years in advance. They understood that 12 lunar months made approximately 354 days, falling short of the solar year by about 11 days. So they developed an intercalation system, adding extra months at specific intervals to keep their calendar aligned with the seasons. This required mathematics. This required understanding that could only come from accumulated observation. This required institutional memory spanning lifetimes. Then came the year, defined by the sun's journey through the stars. The Babylonians identified specific constellations along the sun's path. They divided this path, which we call the ecliptic, into 12 sections. They gave each section a name and associated it with a constellation. They created the zodiac, but they didn't stop at simple observation and categorization. They wanted prediction. They wanted to understand the rules governing celestial motion. And for that, they needed to tackle the most complicated problem of all, the planets. There were 5 planets visible to the naked eye: Mercury, Venus, Mars, Jupiter, and Saturn. Unlike the fixed stars, which maintained their positions relative to each other, these celestial wanderers moved. Worse, they moved unpredictably. Sometimes they travelled in one direction. Sometimes they reversed course in what we now call retrograde motion. Sometimes they seemed to pause in place. How could anyone predict such erratic behaviour? This is where the true genius of Babylonian astronomy reveals itself. They realized that behind the apparent chaos lay hidden periodicities. Venus, for instance, completed a complex cycle every 8 years. Jupiter returned to the same position relative to the fixed stars every 12 years. Saturn took 30 years for its complete cycle, but these were just the obvious patterns. Buried deeper in the data were more subtle rhythms. The Babylonians discovered that certain astronomical events repeated at specific intervals. A particular configuration of Venus and the Sun would recur every 243 years. A series of lunar eclipses followed an 18-year cycle. They called these cycles the Saros, though that name would come later through Greek intermediaries. The Saros cycle, based on 223 lunar months, allowed them to predict eclipses with stunning accuracy. If an eclipse occurred on a certain date, another eclipse would occur approximately 18 years, 11 days, and 8 hours later. Think about what this means. Think about the intellectual achievement this represents. Without understanding the physical mechanisms behind these phenomena, without knowing that the Earth orbited the Sun, or that eclipses resulted from the alignment of celestial bodies, the Babylonians had nevertheless cracked the code through pure mathematical analysis of observational data. They had discovered that the universe operated according to mathematical laws, that time itself could be mapped, that the future could be calculated. This revelation did not come easily. It required infrastructure. It required institutions. It required a civilization willing to dedicate enormous resources to the pursuit of knowledge that might not yield immediate practical benefits. Enter the temple. In Babylonian society, temples were not merely places of worship. They were economic centers, administrative hubs, repositories of knowledge, and schools for the educated elite. The great temple of Marduk in Babylon, the Esagila, employed hundreds of scribes. Among them were specialists in celestial divination, the astronomers and mathematicians who constituted a professional class of scholars. These men lived lives of intellectual privilege and demanding responsibility. They spent years, sometimes decades, in training. They mastered not only the observation of the sky, but the complex mathematics required to analyze what they saw. They learned to read and write in the ancient cuneiform script, itself a skill that took years to acquire. They studied centuries of accumulated astronomical records, memorizing tables of planetary positions, learning the cycles their predecessors had discovered. And then they added to that knowledge. Each generation pushed the boundary a little further. Each generation refined the calculations, extended the tables, discovered new patterns. By the time we reach the Neo-Babylonian period, around 600 BCE, the astronomical tablets produced by these scholar priests had become staggeringly sophisticated. They didn't simply record observations. They contained complex calculations. They included ephemerides, tables predicting the positions of celestial bodies for months and years into the future. They documented the mathematical procedures used to generate these predictions. One particular text, known to scholars as Mul Apin, served as a fundamental astronomical compendium. It listed star catalogues, described the paths of planets, provided rules for intercalating months, and established the basic framework for Babylonian mathematical astronomy. This wasn't a simple observation log. This was a textbook, a reference manual, a synthesis of centuries of accumulated knowledge. But even Mul Apin was just the foundation. The real revolution came later, in the final centuries of Babylonian independence, when the astronomical tablets reached their apex of sophistication. This is when the Babylonian astronomers developed what scholars now call the System A and System B methods for calculating planetary positions. These systems were entirely arithmetical. They didn't rely on geometric models of how planets might actually move through space. Instead, they used pure number patterns. They recognized that certain astronomical quantities changed in predictable ways. They developed algorithms, step-by-step mathematical procedures for calculating future positions based on past observations. Let me give you a concrete example. To predict the position of Jupiter, a Babylonian astronomer might begin with the planet's last known position. He would then add a specific quantity, calculated from tables, representing Jupiter's average daily motion. But Jupiter doesn't move at a constant rate. Sometimes it moves faster, sometimes slower. So the tables included correction factors, multiple correction factors, nested calculations that accounted for the varying speed of Jupiter's motion through the zodiac. The result was a mathematical model of extraordinary power. Using these methods, Babylonian astronomers could predict Jupiter's position months or even years in advance with an error of less than a degree. This level of precision would not be matched in the West until the Renaissance. And they did this for all 5 planets, for the Sun, for the Moon. They created a complete predictive model of the visible universe expressed entirely in numbers, requiring nothing but addition, subtraction, multiplication, and division. No telescopes, no calculus, no computers, just patient observation, brilliant pattern recognition, and mathematical genius. But who were these people? What did they look like? How did they live? We know surprisingly little about them as individuals. Unlike Greek philosophers who left behind biographical details and personal writings, the Babylonian astronomers remain shadowy figures. They worked not for personal glory, but for the temple, for the gods, for the preservation and transmission of sacred knowledge. Their names appear occasionally in the colophons of tablets, the closing sections where scribes identified themselves. Written by Nabu Apla Iddina, son of Shamashiddin, scribe of Enuma, Anu, Enlil. Brief signatures on vast works of computation. Yet in those tables of numbers, in those carefully recorded observations, we can sense their presence. We can feel their dedication. Imagine spending your entire life refining the 4th decimal place of a calculation. Imagine the patience required to track Jupiter for 30 years to verify a single cycle. Imagine the faith needed to believe that your observations, added to centuries of accumulated data, would eventually reveal the hidden order of heaven. They were monks of mathematics, devotees of number, priests who worshipped at the altar of pattern and prediction. And they were successful beyond anything we might have imagined. The proof of their success lies scattered across museum collections worldwide. Thousands of astronomical tablets, each one a testament to their skill. But among these thousands, a few stand out as particularly extraordinary. Consider the Venus tablet of Amisaduqa. This ancient text records the rising and setting of Venus over a 21-year period during the reign of King Amisaduqa of Babylon, around 1600 BCE. It notes the intervals between Venus's appearances and disappearances with precise attention to detail. Modern scholars have used this tablet to help date the chronology of ancient Mesopotamia, demonstrating that these observations were accurate enough to serve as historical anchors across millennia. Or consider the astronomical diaries, a series of tablets spanning several centuries that record nightly observations of planetary positions, weather conditions, and significant historical events. These diaries are so detailed, so systematic, that modern astronomers have used them to study changes in the Earth's rotation over time. The ancient observations are precise enough to detect the gradual slowing of Earth's spin, a phenomenon that adds milliseconds to the length of the day over centuries. This is not primitive stargazing. This is science in its purest form. But before we can fully appreciate the magnitude of their achievement, we must confront the great mystery, the question that will occupy us in the next chapter of our journey. How did this knowledge spread? How did it survive? And why, despite its sophistication, did it nearly vanish from human memory? The answers lie buried in the sands of time, waiting in museum basements, encoded in clay tablets that scholars are still working to decipher. The answers tell a story of triumph and tragedy, of knowledge gained and knowledge lost, of the fragile thread that connects us to our ancient ancestors. London, 1849. The British Museum has just received a remarkable shipment from Mesopotamia. Crates upon crates of clay tablets, thousands upon thousands of fragments excavated from the ruins of ancient libraries at Nineveh and Babylon. The archaeologists who sent them back barely understood what they had found. Ancient texts, certainly. Historical records, perhaps. But the true nature of these tablets would remain locked away for decades, hidden behind the barrier of a dead language that no living person could read. Enter a young man named George Smith. Not a professor, not a gentleman scholar, but a banknote engraver with an obsessive interest in ancient Mesopotamia. Smith haunted the British Museum during his lunch breaks, studying the cuneiform tablets on display, teaching himself to recognize signs, patterns, meanings. His supervisors at the museum noticed his talent. They hired him as a restorer, piecing together broken tablets, organizing the chaotic influx of fragments. And then, one day in 1872, while working through a routine batch of tablets from the library of Ashurbanipal, Smith made a discovery that would rock the academic world. He found a Babylonian account of a great flood, complete with an ark and a hero who survived to repopulate the earth. The similarities to the biblical flood narrative were unmistakable. The implications were profound. But hidden among those thousands of tablets, largely ignored in the excitement over flood stories and king lists, were the astronomical texts, the mathematical tablets, the records that would eventually reveal the true sophistication of Babylonian science. The problem was that nobody could read them. Not really. The basic signs of cuneiform had been deciphered by this point, but the technical astronomical and mathematical texts used specialized terminology, abbreviated notation, and assumed knowledge that no modern scholar possessed. It was like finding an advanced physics textbook written in a partially understood language, with half the pages missing. The frustration among scholars must have been immense. They could see that these tablets contained numbers, calculations, astronomical data. But what did it mean? What were they calculating? What methods were they using? Father Johann Strassmayer, a Jesuit priest and cuneiform scholar, spent decades copying astronomical tablets by hand. He produced careful transcriptions of hundreds of texts, but even he could not fully interpret them. The breakthrough would require a different kind of mind, someone who understood both ancient languages and modern astronomy, someone who could bridge the gap between past and present. That person was Joseph Epping, another Jesuit scholar working in the late 19th century. Epping began to crack the code of Babylonian astronomical texts. He recognized that certain sign combinations represented zodiacal positions. He identified the Babylonian names for planets. He started to understand the structure of the ephemerides, the predictive tables, but his work was slow, painstaking, incomplete. The real revolution came in the 20th century with the work of Otto Neugebauer, the Austrian mathematician we met in our opening scene. Neugebauer brought something new to the study of ancient astronomy: mathematical sophistication. He wasn't just trying to read the tablets. He was trying to understand the mathematical systems behind them. He was trying to think like a Babylonian astronomer. In 1955, Neugebauer published Astronomical Cuneiform Texts, a 3-volume work that finally laid bare the full genius of Babylonian mathematical astronomy. The book was dense, technical, accessible only to specialists, but its impact was revolutionary. It demonstrated beyond any doubt that the Babylonians had developed a complete, sophisticated, highly accurate system for predicting planetary positions, eclipses, and other celestial phenomena. The academic world was stunned. How had this achievement been forgotten? How had it disappeared from historical memory so completely that scholars assumed Greek astronomy represented the beginning of mathematical science? The answer lies in one of history's greatest tragedies: the collapse of ancient knowledge systems. Babylon fell to the Persians in 539 BCE. The Persian conquest was relatively benign. The conquerors respected Mesopotamian learning. The temples continued to function. The astronomers continued their work. In fact, some of the most sophisticated astronomical tablets date to the Persian and early Hellenistic periods. The tradition was still alive, still producing new insights. But then Alexander the Great conquered Persia in 331 BCE, and the world changed. Greek culture, Greek language, Greek science spread across the conquered territories. The Greeks were fascinated by Babylonian astronomy. They borrowed extensively from it. Hipparchus, the great Greek astronomer, explicitly acknowledged using Babylonian observations in his work. Ptolemy's astronomical tables relied on centuries of Babylonian data. But here is the crucial point. The Greeks didn't simply preserve Babylonian astronomy. They transformed it. They reinterpreted it through their own philosophical framework. They replaced the arithmetical methods with geometric models. They gave it Greek names, Greek notation, Greek explanations. And in the process, they obscured the source. Future generations studying Greek astronomy saw the brilliance of Hipparchus and Ptolemy, but had no idea that these men stood on Babylonian shoulders. The original texts, written in cuneiform on clay tablets, became inaccessible. Fewer and fewer people could read cuneiform. The last known cuneiform text dates to 75 CE. After that, silence. The language died. The knowledge locked within it became inaccessible. For nearly 2,000 years, the achievements of Babylonian astronomy were forgotten. Medieval and Renaissance astronomers studied Greek texts, unaware that much of what they admired had been developed centuries earlier in Mesopotamia. The clay tablets lay buried beneath desert sands, waiting. But the loss went deeper than simple historical amnesia. Something profound had been lost in the translation from Babylonian to Greek methods. The Babylonians had developed an entirely arithmetical approach to astronomy. They had discovered that you could model celestial phenomena using nothing but number patterns and algorithmic procedures. They had created, in essence, the world's first computer programs, step-by-step instructions for calculating future states of the universe. The Greeks, influenced by their philosophical commitments to geometric perfection and physical explanation, replaced this approach with geometric models. They tried to explain why planets moved the way they did, not just predict their positions. This led to beautiful theories, to the crystalline spheres and epicycles that dominated Western astronomy for centuries. But it also led astray. The Greek geometric models were less accurate than the Babylonian arithmetical tables. They were more difficult to use for practical prediction. They were, in some sense, a step backward disguised as progress. Only in the modern era, with the development of computational astronomy and numerical methods, did we rediscover the wisdom of the Babylonian approach. Only when we started programming computers to calculate planetary positions did we realize that we were, in essence, recreating what the Babylonians had done 4,000 years ago. Yet the tragedy of loss was not only about methods and mathematics, it was about people, about the human minds behind the tablets. Consider what was required to develop Babylonian astronomy. It required institutional stability spanning centuries. It required a culture that valued knowledge for its own sake. It required resources dedicated to observations that might not yield useful results for generations. It required teachers willing to train students in techniques they would spend lifetimes mastering. It required faith that the accumulation of data, the refinement of methods, the patient pursuit of pattern would eventually reveal truth. All of this existed in ancient Babylon. The temple system provided the stability. The priestly schools provided the education. The cultural commitment to celestial divination provided the motivation. The result was a flourishing of astronomical knowledge that would not be equaled for 2,000 years. And then it ended. Not suddenly, not dramatically, but gradually. As empires rose and fell, as languages changed, as priorities shifted, as the last generation of cuneiform scribes aged and died without enough students to replace them. Imagine being one of those last scribes. Imagine knowing that you are the keeper of knowledge that spans millennia. Imagine looking at your students realizing they are fewer than your teachers were. Imagine wondering if anyone will remember, if your life's work will survive, if the accumulated wisdom of 100 generations will die with you. Some tried to preserve what they could. They translated key texts into Greek. They trained foreign students. They compiled encyclopedic works attempting to capture everything in a single source. But it was not enough. The discontinuity was too great. Too much was lost. For 2 millennia, the clay tablets lay silent, buried in collapsed temples, scattered across ancient library floors, forgotten. And then, in the 19th century, archaeologists began to dig. They found the tablets, thousands of them, tens of thousands. They shipped them to museums. They tried to read them. They struggled to understand them. The rediscovery was not smooth. Early scholars made mistakes. They misinterpreted texts. They underestimated the sophistication of what they had found. The process of decipherment was slow, frustrating, marked by false starts and dead ends. Some tablets were lost in transit. Others crumbled to dust before they could be properly studied. Still others sit in museum basements today, uncatalogued, unstudied, waiting for scholars with the time and expertise to examine them. How much knowledge remains locked in those unread tablets? How many discoveries await? How many ancient astronomers, mathematicians, and scribes are still waiting for someone to read their names, to understand their work, to give them the recognition they deserve? The tragedy is compounded by the fact that we nearly lost everything. If the clay tablets had been written on more perishable materials like papyrus or parchment, nothing would have survived. The achievements of Babylonian astronomy would have been lost completely, known only through vague references in Greek texts. It was clay that saved them, clay that preserves, clay that, when baked or buried, becomes nearly indestructible, clay that allowed ancient knowledge to survive the collapse of the civilization that created it. But survival is not the same as understanding. And this is where our story takes a hopeful turn, because the last century has seen an explosion of scholarship dedicated to recovering and understanding Babylonian science. Mathematicians, astronomers, linguists, and historians have collaborated to piece together the full story. They have discovered that Babylonian astronomy influenced not only the Greeks, but also the Indians, the Chinese, and through them, the entire world. The base 60 system spread globally. The zodiac became universal. The mathematical techniques for calculating planetary positions were transmitted along trade routes, adapted by different cultures, integrated into different knowledge systems. More than that, modern scholars have recognized that the Babylonian approach to astronomy has modern relevance. The algorithmic methods, the emphasis on data analysis, the use of mathematical patterns to predict complex phenomena, all of this resonates with contemporary computational science. When NASA calculates the trajectory of a space probe, when astronomers model the orbits of exoplanets, when physicists use numerical methods to simulate systems too complex for analytical solutions, they are following in the footsteps of those ancient Babylonian astronomers who realized that the universe could be understood through numbers. But understanding the achievement is not enough. We must also confront the uncomfortable questions it raises. Why did this knowledge die out? What does it tell us about the fragility of human learning? What else have we forgotten? What other ancient civilizations achieved heights of knowledge we have yet to rediscover? These questions haunt every scholar who works with ancient texts. They haunt every archaeologist who excavates an ancient site. They haunt every historian who tries to reconstruct the past from fragmentary evidence. Because if Babylonian astronomy, one of humanity's greatest intellectual achievements, could be forgotten so completely that it took 2 millennia to rediscover, what else have we lost? What other brilliance has been erased by the passage of time, the collapse of civilizations, the death of languages? The answer is, we don't know. And that is perhaps the most unsettling realization of all. The answer begins to emerge in the most unlikely of places. A university office in Providence, Rhode Island, 1945. Otto Neugebauer, having fled Nazi Germany, has rebuilt his career at Brown University. He is surrounded by photographs of clay tablets, transcriptions of cuneiform texts, and mathematical calculations that would baffle most modern astronomers. He is about to publish a series of papers that will revolutionize our understanding of ancient science. But this is not a story of one man, one breakthrough, one dramatic revelation. This is a story of slow synthesis, of dozens of scholars across decades, each contributing pieces to an ever-growing puzzle, of sudden insights and patient analysis, of the gradual reconstruction of a lost worldview. The breakthrough came from recognizing patterns, not the patterns the Babylonians saw in the sky, but the patterns in their tablets. Their mathematical procedures followed consistent structures. Their astronomical tables used standardized formats. Their methods, though expressed in archaic notation, followed logical progressions that modern mathematicians could reverse engineer. Neugebauer and his colleagues discovered that the Babylonian astronomical tablets fell into distinct categories. There were goal-year texts, which predicted future positions based on observations from previous years. There were procedure texts, which explained the mathematical steps for generating ephemerides. There were tables of computed planetary positions, lunar data, eclipse predictions. Most revolutionary were the texts Neugebauer classified as System A and System B methods. These represented two different mathematical approaches to modelling planetary motion. System A used what we would call step functions, where quantities change by fixed amounts at specific points. System B used linear zigzag functions, where values increased and decreased in triangular waves. Neither system represented the physical reality of how planets actually move. The Babylonians didn't know that planets orbit the sun. They didn't understand elliptical orbits or gravitational mechanics. But their mathematical models captured the essential patterns with stunning accuracy. Take Jupiter as an example. In System A, the Babylonian astronomers divided the zodiac into zones. Jupiter's speed varied depending on which zone it occupied. The changes weren't smooth, but stepped, discrete shifts from one velocity to another. This sounds crude, but when you run the calculations, when you generate predictions for Jupiter's position over years and decades, the method works remarkably well. System B took a different approach. Instead of zones, it modelled Jupiter's varying speed as a smooth wave function. The speed increased linearly from a minimum to a maximum, then decreased linearly back to the minimum. This triangular wave pattern repeated endlessly. Again, not physically accurate, but mathematically effective. Both systems achieved their goal, accurate prediction of planetary positions. And here's the remarkable thing. The Babylonians didn't choose one system over the other. They maintained both. Different astronomical centres used different methods. Different scribes preferred different approaches. There was a kind of mathematical pluralism, an acknowledgement that multiple models could be valid, that prediction was more important than dogmatic adherence to a single theory. This stands in stark contrast to later Western science, where rival theories fought for supremacy, where scientists committed themselves to specific models and defended them against alternatives. The Babylonian approach was more pragmatic, more focused on what worked than on what was true in some abstract philosophical sense. But how accurate were they? This is the question that modern scholars have spent decades investigating. The answer is astonishingly accurate. For lunar phenomena, Babylonian predictions were accurate to within a few hours over periods of months. For planetary positions, they achieved accuracy within a degree or two. For eclipse predictions, they were correct far more often than not. This level of precision would not be matched in Europe until the Renaissance, when Kepler and others developed modern orbital mechanics. Consider the Venus tablet of Amisaduqa again. Modern astronomers have used computer simulations to calculate where Venus would have been in the sky during the reign of King Amisaduqa. The ancient observations match the computed positions with remarkable fidelity. After 4,000 years, we can verify that those Babylonian scribes were recording what they actually saw, with minimal error or embellishment. Or consider the Saros cycle for predicting eclipses. The Babylonian understanding of this 18-year, 11-day period was so precise that it's still used today. Modern eclipse prediction software incorporates Saros cycle calculations. Ancient knowledge, still relevant, still accurate, still useful. But the triumph of Babylonian astronomy goes beyond mere prediction. It extends into pure mathematics. Because in developing their astronomical methods, the Babylonians also developed sophisticated mathematical techniques that would become foundational to later civilizations. The base 60 system was only the beginning. The Babylonians understood place value notation, the concept that a number's position determines its value. They could handle fractions with ease, expressing them as sexagesimal expansions. They solved quadratic equations. They calculated square roots and cube roots. They developed tables of reciprocals, squares and cubes to aid in multiplication and division. One tablet in particular has captured the imagination of mathematicians worldwide. Known as Plimpton 322, it dates to around 1800 BCE. For decades, scholars debated its purpose. The tablet contains a list of numbers arranged in columns. The numbers themselves seemed random, meaningless, until someone realized what they were looking at. Pythagorean triples. Sets of three numbers where a squared plus b squared equals c squared. The famous relationship at the heart of right triangle geometry, named after Pythagoras, who lived more than 1,000 years after this tablet was created. But it's more than just a list of Pythagorean triples. It's a sophisticated mathematical table, possibly used for teaching or for solving practical problems in surveying and architecture. The numbers are organized systematically, suggesting a deep understanding of the mathematical relationships involved. This discovery sent shockwaves through the history of mathematics. The Pythagorean theorem, that cornerstone of Greek geometry, was known to the Babylonians more than a millennium before Pythagoras was born. And not just known casually, but understood deeply enough to generate systematic tables of examples. What else did they know? What other mathematical insights are hidden in tablets we haven't fully deciphered? Recent scholarship has revealed even more surprises. In 2017, researchers announced that Plimpton 322 might represent a trigonometric table, a completely different way of understanding angles and triangles from the Greek approach. If true, this would mean that Babylonian mathematics was even more sophisticated than previously believed, that it anticipated techniques that wouldn't be discovered again until the modern era. But the influence of Babylonian astronomy extended beyond their own borders and their own time. It spread across the ancient world, carrying with it not just specific calculations, but an entire approach to understanding the cosmos through mathematics. The Greeks acknowledged their debt. Hipparchus, working on the island of Rhodes around 150 BCE, explicitly cited Babylonian eclipse observations spanning centuries. He used this data to refine his own models of lunar and solar motion. Ptolemy, in his great astronomical work, the Almagest, relied heavily on Babylonian observations and calculations, even though he recast them in Greek geometric terms. But the transmission went further east as well. Babylonian astronomy influenced Indian mathematics and astronomy. Sanskrit texts from the first millennium CE show clear evidence of Babylonian methods, adapted and integrated into Hindu mathematical traditions. The sexagesimal system for angle measurement, the division of the zodiac, the computational procedures for planetary positions, all bear the stamp of Mesopotamian origins. From India, these ideas spread to China, Southeast Asia, and eventually the Islamic world. Medieval Islamic astronomers studied Greek texts that contained Babylonian knowledge, and they also had direct access to some Babylonian material through Persian sources. They refined the methods, improved the accuracy, developed new techniques, but the foundation remained Babylonian. When European scholars rediscovered astronomy during the Renaissance, they were, unknowingly, returning to Babylonian roots. The tables of planetary positions, the methods for predicting eclipses, the base 60 system for measuring angles and time, all of this had Mesopotamian DNA. Today, 4,000 years after those first Babylonian astronomers climbed their ziggurat steps to observe the night sky, their legacy surrounds us. Every time we tell time using minutes and seconds. Every time we measure angles in degrees. Every time we use the zodiac, even casually. Every time an astronomer calculates an eclipse or a planetary position. We are using tools first forged in ancient Babylon. But the legacy goes deeper than practical applications. It extends to the very way we think about science and knowledge. The Babylonian approach to astronomy embodied principles that remain central to scientific practice: systematic observation, accurate record-keeping, mathematical analysis of data, predictive modeling, and the refinement of models based on comparison with reality. They showed us that nature follows mathematical laws, that these laws can be discovered through patient observation and clever analysis, that prediction is possible, that the future, at least in its broad outlines, is not mysterious or random, but determined by patterns we can learn to recognize. This was a revolutionary insight. Before the Babylonians developed their mathematical astronomy, celestial events were interpreted as divine omens, unpredictable acts of gods. After the Babylonians, the heavens became a text that could be read, a code that could be cracked, a system that could be understood. This transformation in thinking cannot be overstated. It represents one of the great cognitive leaps in human history. The shift from seeing the world as chaotic and governed by capricious supernatural forces to seeing it as orderly and governed by consistent mathematical principles. This is the foundation of all modern science. And it happened in Babylon, 4,000 years ago, developed by people whose names we barely know, working with tools we would consider primitive, achieving results that astound us even today. But perhaps the most important lesson from Babylonian astronomy is not about their achievements, but about our assumptions. For centuries, Western civilization believed that rigorous mathematical science began with the Greeks, that Euclid and Archimedes represented the dawn of scientific thinking, that everything before them was primitive, pre-scientific, merely groping toward understanding. The rediscovery of Babylonian astronomy demolished that narrative. It revealed that scientific thinking, mathematical sophistication, and systematic investigation of nature arose much earlier, in different places, among different peoples. It reminded us that the story of human knowledge is more complex, more distributed, more multicultural than our traditional narratives acknowledge. How many other achievements have we forgotten or dismissed? How many other ancient peoples developed sophisticated knowledge systems that we've overlooked because they didn't fit our expectations, or because their records didn't survive in forms we easily recognize? The Babylonian astronomers teach us humility. They teach us to look more carefully at ancient civilizations, to take their achievements seriously, to recognize that our ancestors were not primitive but brilliant in ways we're only beginning to appreciate. They also teach us about the fragility of knowledge, how easily it can be lost, how dependent it is on institutions, languages, and cultural continuity. How much effort is required to preserve it across generations. And they teach us about the resilience of knowledge, how even when buried for millennia, even when forgotten and dismissed, truth has a way of resurfacing. How clay tablets can outlast empires. how numbers carved 4,000 years ago can still speak to us if we learn to listen. Today, scholars continue to study Babylonian astronomical tablets. New texts are still being deciphered, new insights still emerging. The project of recovering this lost knowledge is ongoing. With each new translation, each new analysis, each new connection discovered between ancient tablets and modern understanding, we recover a piece of our intellectual heritage. We are, in a very real sense, having a conversation across 4 millennia. The Babylonian astronomers speak to us through their calculations. We answer through our efforts to understand and honour their work. It is a conversation about the nature of the cosmos, the power of mathematics, and the endless human drive to comprehend the world around us. And as we look up at the night sky, seeing the same stars those ancient astronomers observed, tracking the same planets they followed with such dedication, we can feel a connection across time. We are part of an unbroken chain of curiosity, stretching from the first human who wondered about the lights in the sky to the modern astronomers who peer into the deepest reaches of the universe. The Babylonian astronomers were not the beginning of that chain, and we are certainly not its end. But they represent a crucial link, a moment when human understanding took a great leap forward, when we transformed from observers to calculators, from worshippers to scientists, from creatures bound by fate to beings who could predict and, in a sense, control time itself. Their triumph was not just in predicting eclipses or calculating planetary positions. Their triumph was in showing that it could be done at all, that the universe was comprehensible, that human minds could grasp cosmic patterns, that knowledge accumulated over generations could unlock secrets that no individual alone could discover. This is their gift to us. This is what we recover when we decipher their tablets and reconstruct their methods. Not just mathematical techniques or astronomical data, but proof that we can understand, proof that knowledge is possible, proof that the universe makes sense. And in our modern age of technological complexity and information overload, when we sometimes feel lost in a world too fast changing to comprehend, the example of those patient Babylonian astronomers reminds us of something essential. That understanding comes through sustained attention, through careful observation, through the accumulation of data, through pattern recognition, through mathematical analysis. The methods change, the tools improve, but the fundamental process remains the same as it was 4,000 years ago in Babylon. Look carefully, record accurately, search for patterns, build models, test predictions, refine understanding. This is the legacy of the forgotten mathematicians who mapped the stars. This is what they teach us across the silent centuries. This is why their achievement matters not just as history, but as inspiration. The evening light falls across the British Museum's Mesopotamian Gallery. Tourists shuffle past display cases containing clay tablets, fragments of lost empires, messages from the distant past. Most visitors barely pause. Ancient writing, incomprehensible symbols, curiosities from a dead civilization. But you know better now. You understand what you're looking at. Those tablets contain some of humanity's greatest achievements. Those wedge-shaped marks pressed into clay 4 millennia ago represent the birth of mathematical science. Those calculations, still readable, still verifiable, still accurate, speak of minds as brilliant as any that have ever lived. Somewhere in the basement of that museum, in carefully controlled storage, lie thousands more tablets. Many have been catalogued, but not studied. Some haven't even been properly photographed. Each one potentially contains new insights, new discoveries, new glimpses into the Babylonian understanding of the cosmos. The work continues. Scholars around the world collaborate to decipher these ancient texts, to understand their methods, to appreciate their achievements. Each translation adds to our knowledge. Each new connection between tablets reveals more of the systematic brilliance that characterized Babylonian astronomy. But the story of the forgotten mathematicians of Babylon is not just about recovery. It's about recognition. It's about giving credit where credit is due. It's about correcting a historical narrative that for too long privileged Greek achievements while ignoring their Mesopotamian foundations. More than that, it's about expanding our understanding of human potential. When we recognize that people 4,000 years ago, working without modern technology, without modern mathematical notation, without any of the tools we consider essential, could nevertheless create a sophisticated predictive science of the heavens. When we truly grasp this achievement, we are forced to reconsider our assumptions about progress, about civilization, about the capabilities of ancient peoples. They were not primitive. They were not groping in darkness. They were brilliant. They were systematic. They were scientific in the truest sense of the word. And their achievement poses a challenge to us. If they could accomplish so much with so little, what should we be able to accomplish with our vast resources, our powerful technologies, our accumulated knowledge? If they could maintain institutional focus on long-term projects spanning centuries, why do we struggle to maintain attention for more than a few years? If they could value knowledge for its own sake, dedicating enormous resources to observations that might not yield practical results for generations, what does it say about our own priorities? These are uncomfortable questions. They remind us that progress is not inevitable, that knowledge can be lost as well as gained, that civilization is fragile. But they also inspire. They show us what humans can achieve when we commit to understanding, when we value learning, when we build institutions that support long-term intellectual projects. They demonstrate that the pursuit of knowledge is one of the most fundamentally human activities, stretching back to our earliest civilizations. Standing in the ruins of Babylon today, little remains of its former glory. The great ziggurat is reduced to weathered mounds. The temple of Marduk is gone. The walls that once astonished the ancient world have crumbled to dust. 2.5 millennia of wind and rain and human conflict have erased almost everything. But the knowledge endures. Pressed into clay, fired by time, preserved by accident and dedication, the mathematical astronomy of Babylon survives. It speaks to us still, it teaches us still, it challenges and inspires us still, every time an eclipse darkens the sun, following the ancient Saros cycle, every time we measure an angle in degrees, minutes, and seconds. Every time we calculate a planetary position using computational methods that echo Babylonian procedures. Every time we look up at the night sky and see order instead of chaos, pattern instead of randomness. We are experiencing the legacy of those forgotten mathematicians. They changed how humans see the universe. They showed us that nature follows mathematical laws. They proved that careful observation and clever analysis can reveal those laws. They demonstrated that the future can be predicted, that time itself can be mapped, that the cosmic dance of planets and stars follows rhythms we can learn to hear. This is not a small achievement. This is not merely a historical curiosity. This is one of the great turning points in human consciousness. The moment when we stopped being passive observers of the heavens and became active interpreters. When we stopped seeing omens and started seeing mathematics. When we stopped being children frightened by the night and became adults beginning to understand it. The forgotten mathematicians of Babylon gave us this gift, and though their names are lost, though their faces are unknown, though the sound of their language has faded into silence, their work remains, solid as clay, clear as numbers, true as the stars they mapped with such dedication. They teach us that knowledge is worth pursuing, that understanding is achievable, that human minds can grasp the cosmos, that what we learn today can benefit generations far in the future, that careful work, patiently accumulated, builds understanding that outlasts empires, and they remind us of our responsibility. We are the beneficiaries of their work, whether we know it or not. We use their discoveries every day. We stand on foundations they built. We see with clarity they first achieved. What will we leave behind? What knowledge will we create that will speak to people 4,000 years in our future? What will we build that will outlast our own civilization? What truths will we discover that will still be true when everything else we know has changed? These are the questions the Babylonian astronomers ask us across the gulf of time. These are the challenges their achievement poses, not just to remember them, though that is important, not just to appreciate them, though they deserve our appreciation, but to live up to their example, to value knowledge as they did, to pursue understanding with their dedication, to build for the long term as they built. The stars they mapped still shine. The mathematics they developed still works. The patterns they discovered still hold. The cosmos they began to understand is the same cosmos we explore today, with our telescopes and space probes and computer simulations. We are not separate from them. We are their heirs, their students, their continuation. The line connecting Babylonian ziggurat to modern observatory is direct and unbroken, even if it passes through periods of darkness and forgetting. And as long as humans look up at the night sky with wonder and curiosity, as long as we ask questions about the patterns we see, as long as we believe that understanding is possible and worth pursuing, the spirit of those ancient mathematicians lives on. They are not forgotten, not anymore. We remember them now. We honor them with our understanding. We continue their work every time we calculate, predict, observe, analyze. The Babylonian astronomers mapped the stars, but in doing so, they also mapped the human mind's capacity for understanding. They showed us what we can achieve. They blazed a trail we still follow. And the trail continues into the future, toward new discoveries, toward deeper understanding, toward the stars themselves, those same eternal stars that the forgotten mathematicians watched with such patient dedication, learning their rhythms, decoding their messages, transforming chaos into mathematics, mystery into knowledge, darkness into light. Their legacy is not in ruins. Their legacy is in every observatory, every calculation, every moment of clarity when we grasp some pattern in nature and feel the satisfaction of understanding. Their legacy is the scientific worldview itself, the belief that the universe makes sense, that mathematics describes reality, that knowledge is achievable through systematic effort. This is what they give us. This is what we must remember. This is what we must pass forward to those who come after us, just as they pass their knowledge forward to us across 4,000 years of time. The stars endure, knowledge endures, truth endures, and the forgotten mathematicians of Babylon, working by lamplight in ancient temples, pressing numbers into soft clay, watching the heavens turn with patient eyes. They endure too, in our memory, in our methods, in our continuing quest to understand the cosmos they first mapped. Look up tonight, see the stars. Remember that ancient eyes saw the same patterns. Remember that ancient minds decoded what those patterns meant. Remember that we stand on their shoulders, seeing farther, because they showed us how to see. And perhaps if we are very quiet, very attentive, we can hear them still, whispering across the centuries, teaching us, guiding us, reminding us that the pursuit of knowledge is the most timeless human endeavour. That understanding connects us across ages, that what we discover today may echo 4,000 years into the future, just as their discoveries echo to us now. The forgotten mathematicians of Babylon are forgotten no more. They live in every calculation, every prediction, every moment when mathematics reveals the hidden order of the universe. They live in us, and through us they will live in those who come after, as long as humans remain curious, as long as we look up at the stars and ask, as they did so long ago, what patterns lie hidden there? What truths can we discover? What mysteries can we solve? The answers are waiting. in the stars, in the mathematics, in the patient work of observation and analysis, just as they always have been, just as the Babylonians knew they would be. And so the story continues, the eternal story of human minds reaching toward the cosmos, seeking understanding, finding patterns, mapping the stars, from ancient Babylon to the present day, from clay tablets to computer algorithms, from ziggurat observatories to space telescopes. The methods change, the tools improve. But the quest remains the same. We are all children of Babylon. We are all heirs to those forgotten mathematicians. We are all participants in the great project they began 4,000 years ago, the project of understanding, the project of mapping the cosmos, the project of transforming mystery into mathematics, confusion into clarity, wonder into knowledge. This is their gift. This is their legacy. This is what we must remember and honour and continue. As long as the stars shine, as long as humans look up with questioning eyes, as long as we believe that understanding is possible. The forgotten mathematicians of Babylon showed us the way. Now we must follow it, into the future, toward the stars, toward understanding forever. Might have been Bel Apla Idina, or Nabu Zukubkenu, or any of 100 other names lost to time. For our purposes, let us call him the Watcher. The Watcher is not here by accident.